Hello everyone. So this is week 9 and I don't see anyone joined, but I guess it's fine. I do understand it's Sunday. So I'll just get started and you can always go back and have a look to the recorded lecture which would be later uploaded in YouTube. Okay. So this is week 9 and I'm Jagriti, a PhD scholar working with Professor Karla Mercado Shekhar at IIT Gandhinagar, and this is the NPTEL course Techniques of Material Characterization by Professor Shibayan Roy from IIT Kharagpur. Okay. Now, we are here. Well, like last week, we saw the content for week 7 and we solved for week 8. This week, also, we'll do the same thing so that, like, you keep on solving the assignments. I'll also help you solve the assignment for last year for the current week, and then I'm helping you revise you for the content that's being done so that you are reading the content this week and then you're solving the assignment. You're also been given for the same, and then we are also revisiting the lecture material from the last week. Okay. So to start with, I'll just like from last 2 weeks we were not having this kind of PPTs because like I had some resource I was not in a proper setting to show you with. So this week what I'll do is um I have the PPT ready with me. So first the plan is we'll go to the lecture material of week 8. Oh, sorry. And then later we'll continue with it. Okay, so I hope you all have been have referred to it, the content, right? So we have like EDS detector, then we have working principle of ETS, WTS, then we have working principle of it and application and disadvantage. So till now, based on the assignments that we have done so far, I hope that everyone to till now knows that why are we using an EDS and why the WDS one, which one's broadband, which one gives you information about a specific wavelength of a particular element. Now, you should know that both of these techniques are done for only elemental characterization and do highly rely on the characteristic X-rays. Now, from where do these X-rays come from? They come from the nuclei score, right? From one element scores. So hence, we are looking at these two for doing this elemental type of characterization or analysis. Okay. Now, just so we all are on the same page, we'll just have a look on the working scenario and then later the applications part of it, you can also go back and have a look on it because applications are actually the one most that you should be knowing because then you'll also remember it accordingly. Okay. So here's an EDS detector. What it generally has is nothing but a small piece of semiconducting material, either silicon or germanium. Silicon is the one which has been preferred with respect to germanium, but yeah, both of them can be used. Now here in the uh, like way corner right, you see this particular schematic. I like the way they have given it. Like that secondary ones can be used for the topography as the backscatter for the material contrast. I hope my cursor is visible to all of you, right? And then there's EDS or EDX for elemental analysis. So, like you should know or also note down that the depth is helps to propagate, right? The ones which are like the secondary ones they propagate like till 5 nanometers, but then you have backscatter which go till 400 nanometers, and then we have X-rays, the characteristic ones, which comes from deep enough. So those are like till 2 microns in depth, right? So just the depth through which these electrons are coming from and how much are they going and then interacting with the particles are also one thing that you should be aware of, right? Now, your detector is held in a way, this person and these detectors that you have over here, that as many as possible the X-rays which are emitted from the specimen will fall on it. How do they know? Now there must be a specific convergence angle associated with it. Accordingly, as in when you press that one particular detector, for that particular contrast that you want to, it will go and align to that surface. Now, since X-rays cannot be deflected back into a direction that we want, hence the detector must be in the line of sight of the specimen that you want, right? So it's very important. This means that in a single scanning electron electron, it usually occupies a similar position to the secondary electron detected, right? So if it's a single scanning electron, now they have calibrated the system to a point that now they know that where those specific X-rays will go and get deflected. So there only the adjusted or specified position of this detectors is being placed, the EDS detectors, right? Now, in order to collect as many as them, it should be very near to the specimen as practical as possible. And in SEM, it may be possible to place a detector like 220 mm or less because the problems are generated greater with 10 because there also the sample size, the working distance is also very lesser and it is within the objective lens. So it's like directly placed on top of it. It's like that. Now, each incoming X-rays will excite number of electrons into the conduction band of the silicon and will limit is like emit almost identical number of it, like the positively charged holes in the outer shell electron. So let's say if the energy required for each of these is like 3.8 electron volts. So consequently, that many the number of electrons which are generated would be proportional to the energy of the X-rays that is being detected. Okay. So if one would get doubled, the another one is also doubled, but always the energy remains the same for it, or the intensity remains the same for it. Only the number of electrons have been doubled in that scenario. Okay. And if a voltage is applied across a semiconductor, a current will flow as each X-ray photon is being observed in the detector and magnitude that is proportional to the current and the energy will be generated, right? The incident X-ray energy which has been released, now the current would be produced proportional to it, right? So from where will we get number of electrons? So like number of electrons, how they are defined is if you have current that is defined. So current is nothing but it's not a property for a single electron. It arises due to many number of electrons passing through one and another direction. So it's nothing but if you want to find number of electrons, you can simply do it like current divided by the one charge of one electron. Now, since you have included charge of one electron, now you need the time that one particular electron has traveled and the intensity that the electron has. So that is what is included in the entire definition for it. So we'll also see that definition ahead. Okay. Um, Yeah, so there are thin layers of gold necessary on both the surfaces of the detector so that bias potential can be added. Now, you know what bias potential is here? The extra offset voltage that you are trying to add over here. The film of gold on the outer surface of detector must be as thin as possible so that very few ones are observed whereas the rest are being deflected back. And a layer of only 20 nanometer thick will provide adequate conductivity so that they all get passed through and none of them are like deposited in it. Okay. A gold-coated outer surface is usually further protected by a thin window of beryllium or a polymer. Now, we also saw last time that why beryllium was chosen and why it's not chosen. One such specific example we had for it. Okay. Now, despite being so lighter element, despite being made up of Z equals to 4 or carbon, only a few being micrometers thick observe a significant proportion of the low energy X-rays falling on the detector and therefore make the lighter elements particularly very difficult to detect. So this was the question that we had, that if lighter and heavier elements can be detected or not. So lighter elements, for them it's very difficult to get detected through it. Right? No. It is impracticable to detect the X-rays of energies which are lesser with this type of detector, and this therefore eliminates the possibility of all lighter elements which are lighter than sodium. So sodium has like, what's the atomic number of sodium here? I guess till now everyone should know that point since we are doing a course like this. Anyone? I guess I saw someone joining it. Let me check. No, yes, okay. Uh, so it's 11. So the ones which are lighter than that, so we saw that it was 6 or 4 for beryllium. So it won't be able to, it would be very difficult if we want to detect it, right? And they need to be used, such windowless detectors should be used with microscopes which have very extremely good vacuum systems and need a very careful protection from any leaks, right? So the current which flows in between the electrodes when X-ray enters the detectors will last for an extremely smaller, a very shorter time, and is not referred to as one pulse of electrons which is being passed through it. So now when you have something like this, each and every pulse is first amplified, passed to a computer where it has a channelizer. Analyzer will decide that which particular represents which type of energy, and further the pulse is then registered and then it goes. Now the pulse processing time in which one X-ray is detected and the resulting pulse is amplified is shorted by this multi-channel analyzer, and the process must be completed before the next pulse is being dealt with. So it should be completed. Now this pulse time, the time for which this pulse is, or the pulse proceeding limit, will limit the rate at which the number of X-rays can be counted in a way. Now, total time elapsed during analysis will consist of the time for which the detector was counting the live pulses plus the time for which it was ignoring the incoming pulses. Because now it's not that, okay, your detector is one which is the one which is taking hold at the power, hold at some points, whereas sorry, your multi-channel analyzer is the one which is taking halted points and then is characterizing and computing and then generating one specific pulse from it. But it does not mean that the detector is not receiving any pulses till then. So we are the ones which are ignoring that incoming x-rays and the pulses, and we are the ones counting for the time for which the detector is now generating that response. So in determining the x-ray count rate from a specimen, it is therefore the number of counts which are collected for a given lifetime and not the elapsed time, which is important to consider. So we need to consider the lifetime, but not the time which was important to consider. Okay. So this was it. This was like in short how EDS is. What you should remember is only where the what type of detectors are, the material of it, which elements are not considered for it, how the scanning like the path for it, how it goes along, and what else? What else did we see now? Mm, this one is fine, but yeah, you should remember what depends or limits this pulse processing speeds. You should know those things. And this I don't think so, but yeah, why do we have gold on top of it, which increases or limits its conductivity and how much thickness it should be? Now we saw 20 nanometer was the one which will provide you adequate conductivity. So are some terms that are numbers that you should also remember. Then we have this different types of electrons which are coming at different depths, so it's also good to remember those things. Not remember, but you should know that one has like 5 mm, then 5 nanometer, second is like hundreds of nanometer, and then you have some micron step. Yeah, it's very, if someone asks you that arrange in order, then you'll be able to do that thing. Okay. Now we have the second one. I'll give you pause for like 2 minutes and then we'll continue ahead. Okay, so I guess it's been 2 minutes already. Um, we'll start with the second one, that is wavelength dispersive spectroscopy. We'll see the disadvantage of it and how it's being imaged. So imaging in SEM is nothing but it will give us the same thing which we saw previously. It's like how pixels are being processed and how resolution of your image is being generated, how um not magnification, I would say, but how the display size affects us. So we'll see those things. And then also contrast formation in SEM. Okay, so we'll see these four things over here. Now, how the system looks like, and like this is a very beautiful graph where they have shown the direct exact difference in between WDS and EDS. So you see that in the areas in which EDS system performs very poor via lighter elements like poor peak detection, peak separation, background ratio, and the strong points are all the positive points for WDS. So here you can do peak separation effects. You can differentiate this particular element from the background and from all of the rest ones. So, but the only thing about WDSs or the disadvantage for it is like just looking at the images, you it's the thing that you should understand it from there itself that this one won't allow you. It's like it will take lots and lots of time. For one particular scan, only one element is the one that you can detect. So you need a lot of scanning time for it so that it can accurately determine and tell you, okay, this was the element was there. And you can it's like very nicely differentiate in between this background elements and two equivalent or consecutive elements which are there. How it works? Now it works as now whatever X-rays are coming from your specimen will filter it according to the chosen wavelength that we have given, and that chosen wavelength will nothing but lie within the characteristic wavelength of that element, and we allow it to fall on the detector. So now we know that what we are trying to expect there. Now that filtering is being experienced or being achieved by a detector, this particular crystal spectrometer, which will then employ some type of diffraction. So it will allow only the part of wavelength that we want. It will only be passed and others would get bended or will eventually get deflected back to separate the X-rays according to the wavelength. So here you have one takeoff angle. This is nothing but psi or phi here, whatever you call it, are allowed to fall onto the crystal of a known lattice spacing, that is D. So it follows with respect to Bragg's wavelength only, where you have 2D sin theta is n lambda. Now, similarly, you calculate for it, and if it's set to so one theta angle, then only one particular will reach the detector, and hence it would be counted. So you now you need to know that what's the wavelength for that characteristic X-rays. So the detector now no longer needs to differentiate in between the X-rays of different energies because we have already told him that I only want this energy, and since if you only want that energy, you know that what particular element would that that energy correspond to. So then you can perfectly see that if that one energy lies in your specimen sample or not, right? After that, okay, 2 minutes. Yes, after that, in order that as many as possible X-rays are leaving the crystal, which arrive at the detector, the geometry of the spectrometer is chosen such that all are focused on the detector. In order to achieve this focusing event, the specimen must lie on the circle of radius and the radius that we previously saw, this one, the Roland circle, so that everything must be converged over there and we get everything. We get all the, sorry, make it specific to one particular element, one particular characteristic X-ray energy, and that is how it's being referred. Also, that makes up its use to WDS, right? And what's the collection angle, detector efficiency, all those things are there. Yeah. So this is the thing that there are some obvious disadvantage for some qualitative analysis. Only one wavelength of X-ray is detected at a time. A scan of all can require some considerable amount of time. There will not be one particular angle in which one certain line is detected, but there are several different number of angles, so one corresponding to each elemental wavelength that you want to be. Okay. Then there may be as many as like 7 or 8 orders of reflection detected from a major X-ray line or a spectrum, that far more lines that are detected by this. So this will again increase the possibility of signal dilution or signal broadening. In a way, you won't be able to detect it through that particularly. Right. So there are different applications for it to concentrate to calculate concentration of different electrons, and this is how you see. So it won't only tell you that this particular element at this given concentration is present there, but it will also tell you through image that where is it present and how it's present. So this type of imaging sometimes takes time, and you need considerable amount of data for it. It's very good for like it's a very good technique. I won't say good, but like you need to define quantify it, but yeah, in term qualitatively, it's a very good technique. For some quantitative measurement, if you want to do some specific elements and their concentration, especially when it's used in conjugation with some another technique right here. So this is mostly restricted to detection of very lower concentration and detection of lighter element, which ADS cannot do, and the quantitative measurement of the peak heights. Okay, so three like keywords. You should always notice those keywords and have them in your mind. Okay. After that, we have SIM, and then there's imaging in SIM. So SIM and then imaging in SIM. So there's again the same thing. We have how contrast is being formed, the minimum usable beam current, the probe size, and topographic. So I'll give you some time, 2 minutes again, to have a look all the four slides that we just saw now. The applications, disadvantages, how it's through, and then we'll go to the next one. Okay, so we'll then look at this one. Imaging in SIM. Okay, I guess that takes up time and okay, you can somehow have had a look and had an idea that how it was different, how EDS and WDS are now different, right? So now, uh, we have imaging in SIM. So when an image is acquired, the beam will scan the sample surface pixel by pixel, like we are doing raster scanning of it, right? Now in each pixel, the signal is being collected by the detector, translated to a grayscale value. If an image is generated by 8-bit, last time I told you, how many number of pixels will it have? It will have like 2 raised to n minus 1. So if we start from 0, it will be 0 to 2 raised to n minus 1. If it's like 16, we have grayscale value can vary from 0 to like this. Okay, so accordingly, it will also depend. Now, how do you compute a contrast of it? You have contrast for one particular specimen. You find the maximum specimen, the maximum intensity of the signal. You subtract it from that for one particular element and you divide it by the maximum so that you normalize it. So that's how you compute it. The maximum it is. Now, you go from 0 to 255. What do you think it's been going? The maximum one will rely to the whiter one, whereas the lower one is nothing but the darker one. So the higher the grayscale value of the pixel, the brighter the pixel appears in the image, right? The intensity. Now the intrinsic signal from the specimen will vary with the scan position. In order to resolve in between 2 points of the specimen, there must be some two discernible difference in between the signals from these two regions. So What you have right here is there are two signals, probably one intensity, and this is the maximum intensity that you have, and you take a difference from them. So delta S is nothing but difference in between both of them by S max. If you compare both of them, so this is a contrast that lies in between 0 to 1 that concerns to the natural contrast. Now, if a signal that's detected in SEM is not a continuous signal, but for each pixel, now we are deriving number of secondary and backscattered electron that are arriving at the detector at a fixed time period. So these numbers or these events are something which are randomly distributed across time, and if they are detected from particular point on specimen that is n bar, so the noise for it would be square root of n bar. So always there's a thing that if we want to compute noise in a signal, we acquire it as, or we say it as square root of n. Okay, and that's how you represent. Human eye can only distinguish in between 2 points if the difference in between both of them is greater than 5n. So that was number of points that we have, or number of electrons. So this is the noise n. So you do is like 5 square root of n. Okay, so this is what has been derived over here. Hmm. Something's gonna happen today. This eye has been flipping. Okay. Yeah, so this was the thing, that how do you determine the number of electrons? You determine it using the current that's being passed through with respect to the time that it was dwelling it on, or it was looking it on, divided by the charge of the electron. So that's how you compute it. Then you have number of electrons, so it will also be dependent on the charge of the electron. So compute it using that, the Faraday constant. Then also you can do it something as, if it's takes some time for the contrast, you define it with respect to the energy of it, and then you multiply it. So this is the Coulomb electron energy definition, what you might have also have in your class 10th and 11th, where how do you compute the charge of an electron, current intensity, if this other factor is given to you, right? So I hope everyone here till now knows that I'm not talking about this as a Coulomb, but this is nothing but your, what it is, well, this one. So all constants have been written over here. That's your contrast level. That is how we come up to this particular point here. So that's how this is also being defined. So we are trying to determine relationship in between the variables that you already know, so that you can understand them better and you don't need to memorize them again and again. Then what's the minimum probe size for the maximum contrast? So, as in how the probe size reduces, number of electron passing through it also decreases, hence the current also is similar. So for a given detection system, there is a minimum beam current which is required to observe a contrast level. The current will increase as and when the frame time scan time decreases. Sorry. So as and when how your frame scan time will decrease, you'll get more current through that particular area, right? And the minimum probe size you need so for a better resolution image. Wait 2 minutes. I've had let's just say, okay. And then how do you compute it for another level of current? You see it for like with respect to the convergence angle that you have, and you have this two currents. So this is your critical, the offset intensity current for a given contrast level is shown as graphically. So as in how it increases, the value for it also increases. Or you can also see that as in how your probe size decreases. Oh. So here you have contrast, right? And this is the probe size in nanometer which is being increased. Now, as in how your probe size increases, it says F is this, it says F is this. So higher the probe size, I don't know if I can say this, but at 0.5 for all, if you see this one, this one, this one, and this one. So, or if we give like one specific to them, yeah, that follows that for one beam current, you see if the current is constant, so the current will increase as the frame scan time will also increase in that case. So frame scan time, this F, the scanning time increases in this fashion here, and the probe size increases in this fashion over here, which is realistic if you record it for this particular scan rates. So, although the microscope manufacturer will specify the ultimate resolution of an instrument, it's important that you also compute it for your ideal sample. And if you have a low contrast material, the ultimate resolution will be substantially lower, not in nanometer scale, but of course, it would be lower with respect to the ones that you have time to image it. After that, it's just scanning microscopy. So, you see different modes of it. There's a topographic mode of it, the surface features that you see. Then after it, we want some morphological features. So you also tilt the specimen and look at different sides of it. You have also have some stereo microscopy being done. So this is some analogy that they have tried making. Yeah, here's the stereo microscopy. The basic fundamental of this is that if you tilt your specimen in a way that you see from left and right, you see the specimen in both sides, it would remain similar. And in a way, you see a volumetric kind of image. So like these modes aren't generally preferred in SEM, but there are these kind of modes which also still exist and you can see images through it. So backscatter electrons and generated number of electrons detected is a function of both the specimen and the detector geometry that you're trying to look at. Okay. So that being done, then you have mixed analysis for both of them. Here's for topography. Same for topography, how many elements can be used. Now, this was one thing where you had compositional images using the backscatter electrons, right? So this cannot be only tell you information about the surface topology, but also about the composition. Because since they are coming from in depth of the specimen, we saw it like it goes to a depth of around micrometers. So the coefficient is nothing but dependent on the cross section of it. So it will essentially be dependent on the atomic number, and it's recognized here as oscillating voltage. Everything is negative because it's just going, so it's traveling the way back to us. And then here we have taken a positive constant for z cube for the same. And then if you want to combine it, determine the phase of it. So it can be times w. Now here plus nb times the other one. So you have the ones which have been absorbed and then the ones which have been backscattered. So one applies to the weight for it and another applies to the weight of difference in between both of them. So if you can just quickly look at it, can show you. I guess it started here. Hmm. But yeah, probably we'll look at it below as in how we go through. Okay, and then this is a contrast, atomic contrast using the two backscatter coefficient. So always remember the reference goes down. Okay. And then for bases with if we have phases with similar atomic number, the resolution would be poor in that such case. So with that, I guess everything over here is done, and you need to remember things and like you need to know facts of it, and you need to know how things come by. Only the concepts are what something important for this particular week, and then we have week 9 here. Now week 9. Oh, sorry. Here. Now, week 9 is mostly about X-rays and composition. So this is again repeated. Then you have how do you repeat both of them? So mixed and single pixel if everything accounts to 1 or let's say 100%. Then you have some history of it. You'll again go into EDS and then some XRD kind of modes. So those modes are there. So not waiting further, we'll just start with the assignment that if you want, you can pause for a bit and then have a look to the question, have a look to the weeks that we have done so for now. Now we'll have some assignment question answers. Okay. So I'll just wait for another 2 minutes or so. Let's say it's 39 now. We can start from 40, 40, 45. Yeah, 45 sounds good. Okay. Okay, let's start it. So we see the first question is the wavelength range of X-rays used in X-ray diffraction. Sorry, used in the diffraction events is typically about. So for this question, I'd like you to think that what's the interelement spacing, or let's say what's the typical type of distance of the interatomic. So on the orders of what? So accordingly, you can answer it directly. Okay, so the answer for this is this one. Sorry. 0.5 to 2.5 angstroms. So why so? Because yeah, sorry. The typical interatomic distance in the crystalline material are in the order of few angstroms, and X-rays with wavelengths in this range will interact most effectively with the atom, leading to a very clear and informative diffraction patterns. Okay. Now, electron is accelerated towards a tungsten target and an X-ray tube. The resulting photon with a higher energy will be produced when the electron happens what? Now, the electron is being produced and the energy is higher. That means that it would have been collided and then it's getting deflected, right? Oops. I guess the answer is wrong here. Yeah, C is not an answer. This one's also wrong. When it comes to incomplete stop. Oh, when an electron collides with an atom, comes to incomplete stop, it transfers the energy to a single photon the results into a high possible photon that can be produced. Other interaction results in lower one because the electron retains some of its energy. So, well, I guess the answer is C here. When it collides with the target and then comes to incomplete stop, at that point, the higher energy one would be produced and not being deflected. Well, I thought it's being deflected because then only it will go back but and get detected. But okay, I also got confused for this one. If the intensity of a monochromatic X-ray beam is doubled, now what happens to the energy? We saw that the number of energy was proportional to the current for it, how much current is what's produced, but that doesn't necessarily means that energy also doubles. So what happens for this one? So the answer for this is this. It remains the same. Why? Because it will only double the number of photons. Doubling the intensity means that the number of photons will increase, but the energy for each and every photon will remain the same. So it remains unchanged. Okay, next, which of the following is not a characteristic of continuous X-ray spectrum? So does it has a maximum intensity specific or sharp discrete peaks, or it's produced by deceleration, or it has a short wavelength limit? Which one? So the answer is consist of this one. So yeah, exactly. The characteristic X-rays are produced by electronic transition by the atom and that of the target material. So whereas the continuous ones are generated by the deceleration as they interact. So now what was being asked was not a characteristic X-ray, characteristic of the continuous ones. So this was an not a characteristic of a continuous X-ray spectrum. Hmm. Well, this is observed for characteristic X-rays, whereas these are produced and that what happens to them, whereas the continuous ones are generated when it decelerates as they reach the target, as they interact with the target. Okay. Now, which electronic transition in an atom to produce one K alpha 1 characteristic X-ray lines from where to where it jumps? So this one, don't think for long. It's the S shell. Why? Because it's alpha 1 that you want. So that's like a line depends on transitioning from the 2p to the 1s, right? Now, the mass absorption coefficient of a material generally increases with increasing the wavelength. That we know. However, there are some sharp discontinuities called as absorption edges in the spectrum. These edges occur because the energy is insufficient to eject an electron from particular shell, or it is exactly sufficient to eject it, or it is too high to be observed by the material, or it is scattered by the material. So, what happens? So, since it increases, there are some sharp discontinuities. What do the sharp discontinuities refer to? What happens when we have edges? So this one, when it comes from ejected sufficiently enough, so that was when this particular thing happens. So absorption edges are the sharp discontinuities for any material. They occur when the energy is exactly equal. That's when they hit it. And at this energy, the photon is being absorbed and later the another one is being ejected. So there's something as photoelectric effect. Okay. Next, what we have, the wavelength of this K alpha X-ray line for copper is this. If the target is switched to molybdenum, which has a higher atomic number, the wavelength of this will be what? Will it increase or decrease? So, only thing that you should remember over here is how does it depend here? Is it inversely or directly proportional to the atomic number, the wavelength of this particular line? So, in that way, if we have uh, the wavelength for X-ray for copper is this. Now you know the atomic number for copper. You see lines for it. You know the atomic number for molybdenum, and if they have written which has a higher atomic number, so the wavelength for what happened, so it's inversely proportional to it. So what happens? It will decrease, right? Same thing. Now, the width of the characteristic X-ray line is typically what? Is it much wider for the characteristic X-ray line? Okay, much same width, much narrower than the continuous or dependent on the applied voltage. So for it, it is narrower than the continuous voltage. Why? Because they originate for one specific electronic transition in between the energy levels. It's very well defined and it contrasts the continuous one where it's like decelerating ones and you have a broadband spectra of X-ray energies. Okay. Now, in addition to the K alpha X-ray photon emission, when the K shell vacancy is being filled by an L shell electron, which may lead to an emission of which type of electron? Now, which electron is being released from there? We saw that it was a secondary one, but which secondary is this being called as? So if something might come to your mind, yes, it is Agar electron. Why Agar electron? Because the transitioning energy, it can either go to a characteristic X-ray emission or it can be an Agar electron. In the second case, it's much higher energy level causing it to get ejected and it will absorb and get ejected. Hence, it's called as Agar electron. Last question we have, if the current in an X-ray is doubled. Okay, current is double, number of electrons double, not energy, while keeping the voltage above the critical excitation voltage constant. So your voltage is constant, the intensity of K alpha line will be. What will happen to the intensity of K alpha line in this case? So if current is double, the K alpha line intensity would be what? So now you have your signal and that signal is what? Is it proportional to the signal or it's inversely proportional to it? If the current is doubled, what will happen to it? Will it remain the same, decreased by half, increase by 2, or increase by a factor of square root of 2? So here it is increased by a factor of 2. Like doubling the current means doubling the number of electrons which are hitting, which doubles the possibility of ejection of the K alpha photons, thus doubling the intensity of the K alpha line. Okay, I guess that many of you thought about remains the same, but of course it doubles. I just said the answer at the first point. Okay, then if any one of you have any question, I guess if I'll stay in the session for 5 more minutes to see if people join and if they have any questions further. If not, you can always join the discussion forum and you can text in, or else we'll also meet next Saturday. Sorry for this Saturday, like I was traveling from Netherlands, so I didn't get time to take the session online. Hence, I reached today morning at 10 o'clock and then I'm here taking your session. So thanks for being here. Thanks for joining the session. I'll be here. If you have any other further questions, let me know. Okay, I guess then that's it for today. Next week we'll meet Saturday, same time, 5 to 7. Let me know if you have any questions. That time for this current week. Thanks for joining. Thank you.